In the previous video, we took care of the AST printer, right? In the last two videos, I have gone through the visitor pattern and how to serialize our nodes, our abstract syntax tree nodes using the visitor pattern. So we have basically taken care of chapter 5 from that book. All right, now what they want us to do is we have a AST printer class and it serializes the AST nodes, but we haven't created the AST nodes yet. Now they want us to implement the parse command. In the previous stages, we implemented the tokenize command, right? So what the parse command is, it's one step beyond tokenization. It's actually two steps beyond tokenization. The parse command will go through the tokens created by the tokenize command and then create the objects of these classes in precedence. It will read through those tokens and create objects of binary, grouping, literal, and unary. All right, that's what the parse command will do. And then it will use the AST printer from the previous video that we did. It will use that AST printer to print the output to the console. That's what the parse command is. So if my test.logs has this, it should print the parse command should print this. And similarly, if we had true in our test.logs file, it should print it. It should print simply true because it's a literal. All right. The same goes for number literals. If our test.logs only has a number, the number should be printed. Same goes for strings. So if we have a string in our test.logs, it should print the string representation. The parse command, it should print the literal, right? Then we have the parentheses. If we have this in our test.logs file, it's basically a parentheses on a string. So it's a grouping over a string. That's what should be printed. And for unary operators, negation of true should print negation and true in a grouping. And then we have arithmetic operations. So what we need to do now is we need to implement a parser that goes through all the tokens and creates the objects of these and then sends them down to the AST printer. Get the string output, the string serialized output, and then print to the console. That's all we need to do. But we have an issue. We had this grammar, right? We used this grammar to create these classes, right? That's what we did. This grammar was used to identify the nodes of the tree. That's what was the use of this grammar, this simplification of the grammar. But it's not the correct grammar because this grammar is ambiguous. What that means is we haven't taken care of precedence at all. All the operators have the same precedence and are chosen left to right. So if we have 1 asterisk 2 minus 3, then all those operators have the same precedence. So 1 minus 3 into 4. This current grammar is not able to identify that multiplication should happen before the subtraction. It will subtract and then it will multiply, and that's wrong. So this grammar doesn't take care of that. And that's not what we want. We want asterisk and division to have a higher precedence. What that also means is if we have this arithmetic expression, it can be interpreted as in two different ways. So the first is x divided by y minus w, and then the other is x divided by y and minus w. So only one of these is correct. The correct one is this, the second one, but the other one is also valid according to this grammar. So we need to update this grammar. The only use of this grammar was that it helped us, because it is simple, it helped us identify the nodes of the tree. And now that the nodes of the tree are identified, we can sprinkle in some more rules to bring in precedence. Right? The other thing that this grammar is missing is associativity. And what that is A minus B minus C is basically equivalent to uh, A minus B and then minus C, right? So the minus operator has a left associativity. That's what associativity means. But the equal operator is supposed to have right associativity. It's basically supposed to be equal to A equals to B equal to C. What B equal to C results is the value of C. So A will then be assigned the value of C. The equal operator has right associativity. These are two things that grammar is missing. Let's define the precedence of the language. B and C. And the lowest precedence in our language is for equality, not equal to. So we can have expressions on the left and the right side of equality, and first those expressions are evaluated and then equality is evaluated. Then the next operation that has a higher precedence than equality is comparison operators, which are greater than, equal to, less than, equal to. Then we have term, uh, which is basically the minus and plus operators. The book calls them term. And then we have factor. Factor are division and multiplication. And then we have unary. So the unary has the highest precedence. So first of all, unary is evaluated, then a factor, then term, then comparison, and then equality. We need to update our grammar to reflect this precedence. So the grammar we had right now was useful for identifying the nodes of the tree, but now we need to sprinkle in some more rules to take care of this precedence. If our tree construction is recursive, the last thing that we check, that is the thing we check at the bottom of the tree, is the thing that will be created first, which means that has the higher precedence. As we go down the tree, the leaf node is evaluated first. So the leaf node has the highest precedence. So that's why unary will be at the bottom, right? Because it has the highest precedence, and equality will be at the top. Uh, what that also means is when we go to create a term node, we need to first check that can we create a factor node. And before checking if we can create a factor node, we should think if we can create a unary node or not. That's what we need to check, right? Basically, we need to check that if we can we create an object of unary, all right? And as our language also supports BODMAS, so this grouping, which is right up here, it should also be at the bottom because brackets have the highest precedence of all, right? Let me add that to brackets. So brackets has the highest precedence. So it should be at the bottom of the tree. What that means is brackets will be at the bottom of the tree. What else do you think will be at the bottom of the tree? What else should be at the leaf nodes of the tree? It should be the literals. So the grouping and literal will be merged into one rule. So let's do that first. My bad. CFG, right? So we had this literal rule in our language, and to this literal rule we will add the brackets, all right, because I told you brackets will be at the bottom of the tree. So let's do that. This will be the root nodes of our tree. This is the condition where our recursion breaks, all right. That's going to be the primary. And then, as I told you, equality has the lowest precedence. It should be at the top of the tree. So whenever we start parsing an expression, we need to check if it's an equality. And before, like I told you, uh, before checking for a term, we need to check if we can create a factor, and before checking for a factor, we need to check if we can create a unary. Similarly, before creating an equality, we should check if we can create a comparison. In our language, we can write expressions like a equal to b, a equal to b, equal to c. So we can tail these expressions. One can follow the next one. So we need a rule that can represent this expression, and that can be done using the notation that's given in the book. All right, let me just copy that and let me explain that. What this means is basically the asterisk is like a regex. So a comparison uh, and a comparison can be followed by another equality, and it can keep going on. That's what this asterisk mean, right? In regex, that's basically what it is. And we have comparison here because before creating an equality, we should check if this equality can actually be a comparison or not. If it can be a comparison, the asterisk here can also represent zero of these. So then we won't have these tailing the previous comparison on the left. If an equality can be a comparison, then it will be a comparison, and none of these will be created, and none of these will be checked. All right, that's what basically this rule is. The rule for comparison is quite similar. Instead of comparison, we have term. When we get to a comparison, we check, can we create a term? If we can create a term, then well and good. We won't go here. This rule will satisfy that because we have an asterisk and we can have zero of these following the term. Same goes for term and same goes for factor. All right, so let me just copy those. Similarly for term, the term, when we go to a term, we will check, can we have a factor? If we can, this asterisk say that zero of these need to follow the factor. Similarly for factor, when we get to a factor, we check if we can create a unary. If we can, then zero of these follow, and then the unary rule. So the unary rule is a little different. All right, this is what the unary rule looks like. What this rules, what this rule states is that we can nest unaries. All right. So this negation of true will be equal to false, then negation of false will be equal to true, then this negation of true will be equal to false, then this negation of false can be equal to true, then this keeps on going till we get to a final. Till we get to a final unary, and then this will be equal to false. All right. So we can nest these, which is why a negation, a unary has an operator and then again is followed by another unary, or it can be a simple primary, right? If a unary is evaluated, it becomes a primary. All right, and this literal rule will be called a primary, and this is a fully non-ambiguous in terms of precedence context-free grammar that can be implemented in our parser. All right, so let's go ahead with it and implement the parser. So we'll start with the main class. They want us to add the parse command, and we need to add that to the main class. We only have the tokenize command in the main class right now, and it looks something like this. So right now we're checking if the command is not tokenize, then we're just running the run. But now we'll have multiple commands that we need to support. So what I'll do is, if command is equal to tokenize, let me move this out, and in that case I will call runner dot tokenize, and else if command dot equals parse, in that case I will call runner dot parse file name, and in both these cases I return and then if we don't have any of these commands, in that case we exit unknown command. All right, so we need to create these methods. Let's do that, and let's create the parse method as well. So in the runner class, so now in the runner class, we have this common functionality of reading the file contents. So we should extract this out in a method. Right click, refactor, extract method, and call it get file content. All right. Uh, we get the file content. Now it's extracted out. And we do not need this run method anymore. Let's control X and paste it in tokenize. We get the file content, all right, and if content is equal to null, we return, and we do result. We in the parse command we don't do this right here. Instead of printing the tokens to the console, we will create another class called the parse class. So we need to create the parser class. I'll create the parser class at the AST level. I'll call it parser. All right. And now in the runner class, I will create an object of parser, new parser, send it the tokens. So, but we only send these tokens down to the parser if we do not have an exception from the lexer. And we can check that with this. Now we'll create another method in the parser called the parse method. Like we have the lexer.scan method, parser dot uh, parser dot parse, and let me just make this private. And this parse method will return to us an expression, the root expression node. All right, let's create this method, and in the runner class we will check if this expression is not null, and if this is not null we will serialize it with the AST printer class. So if E is not equal to null, we'll create an object of AST printer, and we'll call it just AST printer new AST printer, and we will serialize it with dot print, and we'll send it an E. Otherwise, if it is null, then we don't do it. In that case, we exit out with the system.exit. So let me just copy this and write here else paste. In that case, we simply exit out of it. Now let's think about exception handling a little bit. In the lecture, we were returning a result class, and in that result class, it was a wrapper over the expected resultant tokens and the exception. Can we do that with the parser? If we do that with the parser, the moment an exception is occurred, it will return an object of result class. But that's not what we want. Why is that? Because whenever we parse through a list of tokens, we want our parser to report all of the exceptions that are encountered, not just the first one. If we were to return the exception the moment we encounter a parse exception, if we want the parser to return at that point, in that case, any exception that might have occurred in the future won't be reported to us. So we will handle the error differently in the parser. What we will do is this parse method, whenever it encounters an exception, will set a flag true in a runner class. What that will do is it will create an object of parse exception and set it to this field. Let me create that private parse exception, parse exception, let's call it parser exception, because parser exception already is a thing. Parser exception, and let me create that class as well. Let me just copy it. All right, and let's get back to the another class, parse exception. Let me import it, and let me create a setter public void set parser exception. It takes a parser exception pe, and this dot parser exception equals to pe. All right. So what we want our parser to do is, if it encounters an exception, we want to report it, and then we want it to set this variable to not be equal to null. And what that will do is, when we get to evaluation, we will have another method similar to this parse method, and that will, instead of printing to the output, let me give an example, evaluate. All right, and instead of printing, what we will do is we will call the evaluate on the expression. All right, but that we will only do that if it is not equal to null, and the parser exception, why do I get an error? Parser exception is also not equal to null. Oh yeah, we need to make it static. All right, and instead of this we will do this, because it's a static variable, and we will only evaluate the expression if the parser expression is also not equal to null. So that's going to be the use of this parser exception. We don't have it right now. Okay, so its default value should be equal to null, so let me just set it to null. Okay, we want this parse method to go through the list of tokens, create an AST, report all the errors it faces while creating the AST, and set a value to this parser exception. That's what we want this parse method to do. Okay, so now let's finally get to the parser. In the parser, we have a list of tokens, and just like in the Lexer, we had a list of, let me show that to you. In the Lexer, we had some string, right? And we had some utility methods that let us operate on this string. Just like that, we're going to create some utility methods that will let us operate on this list of tokens. And in the Lexer, we had some pointers, right? The current and start. Just like that, in the parser, we're going to have pointers as well, and we will use that pointer to peek and get the next token, etc. So let's create that. Let's create a public int current equal to 0, and we after that we need a method that will get us the current token without moving forward. So we will peek into the list and get the token the current pointer is pointing to. So token private token peek, and this will return tokens dot get of current. And we will also create a utility method to get the previous token. We will call that previous, returns tokens dot get of current -1. And we also need one method to tell us if the list if we have come to the end of the list. So I will call that is at end. And if you remember in the Lexer, before returning the list of tokens, we added an EOF token. So we can check if we are at the end by checking if the current token is equal to EOF. So we can return peak dot type is equal to, and it can be EOF. Those are all the utility methods that we need uh, to operate on the list of tokens. We also need one more. It's kind of like peak, but it moves the pointer one forward as well. So private token and advance, and we only move forward if we are not at the end. So I can check that with if not is at end. If that is not the case, we can move forward and return the previous one. After this, we need a method to check if the current token the current pointer is pointing to matches a type we are sending down to it. So we can check that with boolean check current type, and we will send it a token type. Let's just call it type. Oops, my bad. Token type, and right here we will if we are not at the end, we will only check it if we are not at the end. If not is at end, uh, sorry, if we are at end, I can simply return false. Otherwise, I can check the type of the current dot type to be equal to the type. That checks for us the type of the current token. We also need a way to be able to match multiple tokens and move forward. All right, and we will create a method for that as well. I'll call it private the return type boolean in case we match, and let's call it match current token and current token, and this will take a list of token types, and we can use the spread operator for that types. And for each token type in types, if we match the current token with this type, we can move ahead and return true. So we have a method to move ahead, and I can return true. But if no type matches, in that case we will return false. Now we'll take one rule of our context-free grammar at a time and implement those rules one by one. So whenever we start parsing, we'll start parsing. We expect there to be an expression. So we will create this expression method. And the expression rule is quite simple. It simply expects right now it to be an equality. So what I'll do is I'll return an equality. All right. We need to implement this equality method. But before doing that, I want to implement this primary method because it's quite simple. It's the easiest, like it's the terminal node. It's the function where our recursion will end. So I should write this base case first. So let me create that method as well. Private expression primary. All right, primary, and let me move it up as it's the base case. So let me move it even before expression. Let me, yeah, it's the base case, so it should be before expression. So in the primary method, if we match the current token to be a false, a boolean, if it's a false, what I can do is I can return a new literal, and it can be and its value will be false. Similarly, if it were true, its value will be true. So let me add that. And if it were null, we will return a literal of type nil. So this does it for us. If none of these cases are true, the current token may be a number or a string. So we can do that. We can check that by using number comma string. If any of these matches the current token, in that case, what we can do is we can return a new literal, and its underlying Java type, Java object can be dot literal. All right. And if none of these is true, then according to the rule, we have, say we match number, string, true, false, nil, and now it may be a bracket. It may be a grouping. So in that case, what I'll do is I will check if the current token is actually a bracket. So if match current token, if it is the left parent, if it's a left parentheses, in that case, we have an expression nested inside of it. Expr, and it's going to be an expression. So expression and expression, and after that we can return a new grouping, or and the nested expression will be the expr. But you see, after we have checked the current token to be left parent, we consume the nested expression. The closing parenthesis is still left, so we need a way to be able to consume the leftover parentheses. All right, so we will create a method called consume, and this will consume the right parentheses for us. Right underscore parent, and let's just call it token type dot right parentheses. And what if there is no right parentheses? In that case, I want the consume method to throw an error. And what should be the error message for it? We will also send out the error message for it. So right here we expect closing parentheses after the expression, right? So after expression, that's what we want here. So let's create this method. This is also a utility method kind of utility methods we were created earlier. So let me move it up. All the utility methods are now together. So in this method, what I'll do is I'll check if the current type is of token type. In that case, I can move ahead. All right. And I can also advance. Okay. Let it return a token. Let it return the current token. If it matches the current token, we move ahead and return. But if it doesn't, then we get the current token type. Current token type is peak. And right here, I want to throw an error. So I will create a wrapper method that will throw the error, that will return the error to me, which I'll throw. And that method will also be responsible to report the error on the system.error. Output stream. So I will create this method and I'll call it report. The reason I'm calling it report is because it's called report in the book as well. And I will also give it the error message that I want. So right here, I expect an expression. No. Oh, sorry. Right here, we already have the error message down right with us. We already sent it the error message, and this error message will be used right here. So let us create this method. This method is not going to return an exception, it's going to return a parser exception, the exception class we created earlier. So it's going to be parser exception. And in this method, I want to be reporting the error to the system.error output stream. So there is a particular format CodeCrafters expect you to print the error in, and I'm not, yeah, it's syntactic errors right here, just exploring. So the format is this. So we need the line number here, and fortunately we have the line number in the token, so I can get it from there. Int line equals to, we have the token right here, peak dot line, right? And now the other thing is, if the error is at a particular line, then we print it. And in some cases, if you try to run only with that, it will throw an error because that's not how the book does it. Uh, in case the current token is of type EOF, in that case we need to print that the error is at end, not at the line number. So we need to handle that conditionally. If if peak dot type equal to token type dot EOF right here. If it's EOF, in that case I want the error message to be different. Otherwise, I want the error message to be different. So let's create a string variable to help us with that. Uh, in where, in this where, I will say where the error is at. If the token is EOF, then the error is at end. Otherwise, the error is not at end, it's at the line number that we already have. So let's say that at, and then this plus token dot lexeme, no, sorry, peak dot lexeme, let me just rename it, it's very confusing. Refactor rename token dot lexeme, like so. See, because if you see error at, we see error at and the token, and if the error is at the end, we say error at end instead of this. So that's what we are saying. After we have decided that, I can actually print the error to the output stream, to the error output stream. So println, and in here I will print, let me just copy that, it's pointless to reason about it. This is a particular format that they tell us to use, so this is the format. After this parser exception, I will create the exception, new parser exception, and in here I'll give the error message like so, and I'll give the message that we had. Okay, and after this, like I told you, I want to be able to, oh yeah, since my bad, since the runner class is in the default package, we won't be able to import it directly. So I will create another package called runner and move runner class to that refactor. And in here now I can runner dot is that private? Let me make it public. The setter that we created, it's public. Static. Yeah, it should be static. Dot set parser exception, and to this I'll send the exception. There is a typo in the name, let me refactor it. IntelliJ will do that for us. Type rename to exception, and with this I can return the exception that we created right now. Okay, so this reports, then consume throws it. Consume is being used here. All right, this throws the error. So in case the current token type is not right parentheses, then it will throw an error, and the primary won't be returned from it, the grouping won't be returned from it, and that's exactly what we want, right? So whenever we call this primary, we need that in a try catch block. What I'll do is, instead of keeping every method in a try catch block, I'll keep only the main method, the entry point. Where is the parse? We had a parse method, right? That is the entry point into this class. Where is it? Where is it? Where is it? Yeah, right here. So I will keep this in a try catch block. Try catch, and it will be catching parser exception, and then I can return null in case an exception was thrown. All right. In the primary, if none of these cases is true, if we don't even see a grouping, in that case I definitely need to throw an error. I will call report method because it will create the exception and report it to the error output stream as well, and I will say expect expression. Okay, that completes the primary rule for us. If you see, we have handled all of these cases and thrown an error if none of these is true. Now we have the equality rule. So let's just copy what the rule looks like and keep it in a comment right here. Okay, so our equality rule is basically a comparison and then optionally many other comparisons. That's what it looks like. So equality can either be expression, it can, and I will just return it. Wait. So equality can either be a comparison. We don't have a method to calculate comparison right now, but we will create it soon. Let me just create it anyways. Comparison. Yeah, comparison. So an equality may be a comparison, and then optionally we may have other comparisons as well, and that optionally depends on whether or not the next token is a not equal to or a double equal to, and we already have a method that checks the token. So the current token, uh, we already created that utility method, so I'll use it. So I will match the current token to be uh, bang equal or bang 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 underscore. Do I not have a double bang? Oh, sorry, bang and equal equal. Yeah, equal equal. Let me control F token type dot star import static. Now right here I also need to import the token type. Okay, so import lexicon dot token type, we need that as well, and right here I can simply use EOF. And where else? Right here I can use it directly. I have imported it statically. Right here as well, right here as well, and right here. With this, if the next token is a bang equal to or a double equal to, in that case, what I can do is I can consume the token, and that will be an operator. So no need to consume because the match current moves one ahead as well. We advance. So in that case, I need to get the previous. That will be the operator. Then the expression that may follow again may be a comparison. So expression, right, it's going to be a comparison again, and now I can I can tail them one after the other using the operator. So what I can do is I can create a binary object. So expr is going to be a new binary, and in here the operator is going to be the operator, and then we have the left side expression is expr and the right side expression is right, and this is what we're going to be returning. So this will be the equality, this will be the method that parses the tokens and creates an equality node of the abstract syntax tree. Now, if you take a look, the comparison, the term, and the factor, all the rules are quite similar to each other. Only the only difference is that we are checking for different operators right here. So let me just copy the rule, and the code is going to stay quite similar. Only the underlying operators that we're checking for, and the next function in the recursion is going to change. So what I mean by that is comparison is a term, right? And we don't have that method yet, and it right here it should also be a term. Let me create that. And these tokens are going to change. We are going to have a greater, we are going to have a greater equal, we are going to have a less, and then we are going to have a less equal. We do not have an equal in comparison. That's all the thing that we need to change. We don't need to change anything else. Let's grab the next rule for the term and paste it in the term method. And all of this code is going to remain the same. So the term goes into a factor, right? So let me call the factor right here. And only these operators are going to change. So it's going to be a minus, and then it's going to be a plus. And we need to create this factor method. Let's grab the rule for the factor. It goes into a unary. We do not have a unary method yet. We'll create it right away. Let me copy the code from above and paste it down below. Instead of factor, it goes into a unary, and the operators we have are division. What was the operator? What was the operator? Star and then a slash, a star and slash. My bad. So this is going to be a star and a slash. Let me see if that's correct. Yeah, star and slash. And we do not have a unary, so let's create the unary. Let's copy the rule for unary. Now the unary rule is finally different from all the others. The unary rule is not recursive like the other ones were. We do not need a loop in here, because if the unary nests, it just it doesn't have an expression. It doesn't have an expression that we need to consume. It's just an operator, then finally an expression. So we're going to have a ton of operators, and that is simply a tail recursion. We do not have other things that we need to do in between of the recursion. So what we'll do is we will simply check if the current operator is a unary operator. So that is match current token, bang or minus. If that is the case, then we will check if the next thing is a unary or not. Token operator equals to previous expression on the right is again a unary, maybe a unary. And if that is the case, then return new unary operator and write. Okay, and you see, if we do not have any other minus or bang after the initial minus or bang, then it is going to be followed by a primary, right? So that is the case. That's why we are returning a primary from here. And I think those are all the rules. I think that is it. Uh, Let us just try and run it. What happened? Did it work? Tests failed. What is the issue? Uh, Expected line number 1 on std out to be true, got nothing instead. So there is something wrong in our primary, I guess. Let me see. Primary. Where is primary? Yeah, right here. So if it is true, then we create a new literal out of it. Let me just try it on my own. True. And let me edit the configuration. And instead of tokenize, I'll pass in the parse command, apply, OK, and run. It didn't print anything. Why is that? Let me debug. Okay, so the control comes here. Does the control come here? It does. So let's step out of it. And we return. Okay, so let us step out again. Let us step out again. And we're going to step out 3 to 4 times. Equality is being called here an expression. Let's step out of expression. Parse, let's step out of parse. Let's move forward. Expression is literal of type true, so there is an issue with our AST printer. Is that the case? Okay, so the issue is in our printer. Why is that? Visit binary, visit literal. Where is the visit literal? Value dot to string. Does the control come here? It does. Expression dot value. What is expression dot value? Expression is true. It returns to string, right? It should. So let's step out of it. Step out. Let's step out. It should have printed, right? But it did not. Why is that? Let me go into the print method, and right here let me string result equal to, oh my bad, sorry, it just returns it, it doesn't print it. So right here I need to put it in a shout. Oops, such a silly mistake. There it is. Let me try to push it again. Let's see what the logs say. Does it work? It should work. At least all the literals should work. It does. So what I'll do is I will click through the stages for all the literals. This one should work as well. Let us see. It does. Then we check the string literals. Does it work? It should. It does. So I won't click here. Why? Because I want to show you guys something. Let's go to chapter 6 of the book and come down to challenges. So if you see, we have 3 challenges here. And the first challenge is we need to add the comma operator. The second challenge is we need to add the ternary operator. And then the third challenge is that we need to add error productions when a binary operator appears without a left hand expression. If there is a binary operator like plus and there is no left hand expression on the left side of it, in that case we need to throw an error. Okay, so to me this seems very important, other than more than these at least. So we will add that. We will add that error and then we'll add the comma and ternary as well. Then we'll remove the comma. We will remove the comma because the issue is right now we won't see an issue, but in the future when we implement function parameters and function arguments, in that case the comma operator will throw an error, will cause issues. It won't be able to parse all the arguments correctly because the arguments are also separated by commas and simple expressions can also be separated by commas. So that is why we will then remove the comma, but I'll show you how to add the comma. So I think to handle function arguments and function parameters differently, we would need to change the comma rule, but I didn't bother with it. I simply removed it because it didn't seem very important to me. I didn't want that in my language, but I do want ternary operators and I do want errors in case somebody writes code like this. I don't want that. It seems bad. So I want my parser to throw errors in that case. How do you think we do that? How do you think we handle checking that there is an expression before parsing the operator? It's quite simple actually. Before actually doing this factor, I will check if there is something to factor. Like if the current token is a minus or a plus, in that case, I will check if there is something on the left hand of it. If not, then I'll throw an error. That's what we will do basically. So let us create a method to help us do that. We will create a method called handle binary operator without left expression. Quite verbose, but we need it. Okay, so private void handle binary operator without left expression. So it can again take a number of token types. So, and we will iterate through those for token type and types. All right. If we already have a method for it. If the token that the current is pointing to happens to be of the type in these types, in that case we know that there is an issue, that was supposed to be something on the left side of it, but there isn't. We are simply pointing to the operator. We're not pointing to the left hand expression. There should have been a left hand expression, but there is not. We're simply pointing to the operator. So we missed out on something, and that is why we will consume the operator. We'll call advance, and now I will report an error. We already have a method to do that. Report, and in here I will send the operator to point to it, and the error will be, let me just copy it. The error is going to be missing left hand operand for this operator. This is the error, and we're not going to throw because I want my parser to continue parsing, because somebody may give something like this 1 minus 3. So it is true, we do not have a left hand operator right here. We only have a left hand expression right here. We only have an expression on the right hand, but the right hand expression in itself needs some parsing. So if the expression in here was plus 3, that again is incorrect. So I want my parser to throw the error multiple times, to report the error multiple times. That's why we're not actually throwing the error, because throwing the error would break the control flow and control will come out of the parser. So that's why we're not throwing it right here. And I'm going to use this method in all of my methods that are parsing binary expressions. So unary is definitely not a binary expression. Factor is. So before before parsing through the tokens, I will call this method with the token types that are being considered in this method, which are a star and a slash. And then similarly, right here, I'll call it. Should I call it with a minus? No, minus is a unary expression as well. That's why we send here only a plus. And is comparison a binary operator? It definitely is. We cannot compare a single thing. We need multiple things to compare. That is why we need this right here as well. The other thing is that we're creating a binary. So it's quite obvious it is a binary. And similarly, equality is a binary. Let me copy it, paste it. And the operators in the equality are these. Let me paste them right here. And I think that is it. That handles all of those cases. Let me show that to you. So if we have a divide by 3, should throw the error. It should report the error. See, error at the operator missing left hand operand for divided by 3. And it won't work for minus because minus is a unary. See, it works. So that is one of the challenges of the book solved. This challenge is solved. Next thing we are going to add commas and ternaries. To add commas and ternaries, we would need to make some changes to our context-free grammar. What is that? What are those changes? So a comma happens to have a higher priority than equality. So comma actually comes right here. So damn. In terms of operators, comma is right here. Control Z, Control Z. What the hell? Why are all the... Arey yaar. Damn. Let's leave it out. Basically, comma is going to be right here, and then ternary is going to be right here. So commas and ternaries have higher precedence than all of these other operators. Okay, that is why our rule is going to reflect that as well. Before equality, we are going to have a comma, and the comma rule will look something like this. It's going to be quite similar to others. And we will create another rule called the assignment rule. Okay, and assignment is simply going to be assignment right now will only go to equality and won't do anything else. Like expression was going to equality. That's it. That's all we are going to do. Equality right here, and assignment is just going to be like all the other rules. We just have the operator, which is the comma, and then we have the assignment again, and it may be followed by optionally multiple assignments. So that is why the star right here. So this is the rule. Okay, but that is the rule only for commas, but we also want to add ternaries. To add ternaries, turn this to a ternary. Copy it, paste it, ternary, and ternary rule looks something like this. Let me just copy it for you. See, I made these rules up by myself. So I'm going to copy paste. Assignment. The assignment may be optionally followed by a question mark. The question mark will then be followed by an expression. The expression will be followed by a colon. The colon then again may be followed by a ternary. Okay. Oh damn, we may have a ternary here as well. So it should be a ternary. Oh, my rule was wrong. Anyways, we'll correct that. We'll fix that. Okay. And this may be followed. This question mark right here means it must be followed at least once by these. But we'll change that to a star because the ternary may be an assignment or may simply be an assignment. It may not necessarily be a ternary. So that is why. So let's add these to our parser. Okay, so for comma is going to be quite simple. Uh, expression right here. Okay, so our rule expression used to go to equality, but now expression, oh damn, it should go to ternary. Should it? And let me see. Wait, give me a moment, guys. Oh yeah, sorry. It goes to a comma because comma has a higher precedence than ternary. So that's why. Lesser precedence, sorry. So that's why comma is going to be right here, and that is the reason expression goes to a comma now. So expression is going to go to a comma now. Let me create that method. Create method. And what does the comma rule look like? The comma rule may be a ternary followed by optionally other ternaries. So this is the comma rule. Okay, so it may be a ternary, but it may not be. And also, comma again is a binary operator. So, and right here we need a token type, but we do not have that token type yet. We do not have commas right here. Oh, we do. Did I add that? Yeah, I did. Okay, so we're good. Uh, so it was not required of us, but I added it by myself. Okay, so comma, we're checking if right here we're checking if comma is being put without actually there being a requirement for the without there being a left hand expression. So expression. Now this expression may be a ternary, and we do not have that method yet, so we'll create that as well. So this rule, the code essentially is going to be the same like all the other because the rule is the same. So let's just use it. My bad. I'll paste it below. And ternary, it's going to be ternary. And right here, it's not going to be these. It's going to be a comma. And let's create this method. So in the ternary, the rule looks something like this. The ternary operator again is does require a left-hand expression. There cannot be a question mark without there being a left-hand expression. So question right here. Then the ternary operator goes into an assignment, and the assignment basically goes into equality. So we do not need it here. We do not. I'll simply call equality right here. Equality, and it may be a ternary and then again a ternary. Okay, we're good. So it's going to be an equality. So we're going to use the code from, no, we're not. So this rule is a little different from the other rules. So expression and equality. So if the current token is a question mark, if it is a question mark, only then it's a ternary, and only then we're going to parse the true branch and the left branch. So expression true branch may again be a ternary, right? And then and after the ternary there is definitely going to be a colon, so we need to consume it, and if there isn't a colon then we need to throw an error. So colon, and the error in case it doesn't exist is, let me just copy it, colon expected after question mark of ternary expression. That is going to be the error. I made those errors up. They are not asked of us by CodeCrafters or the book, but I'm keeping them. The operator is previous. Does consume return the token? It does. So what we can do is instead of this, I can simply okay. And the false branch. Now we need the false branch of the ternary operator. False branch. It again can be a ternary, and right here Now we can finally create the ternary expression, but we do not have an AST node for it yet. All right, we do not have something that takes two expressions, that actually takes an expression and then two optional results of the expression. So we need to create another expression for it, and I'll simply call it the ternary. So let me do that. New Java class ternary, and this ternary is going to extend the expression. Let me implement methods except, and it's going to call visitor dot, we do not have it yet, so let's create it, visit ternary, and I'll pass it this expression visitor. Okay, and where is it implemented? This is implemented in AST printer. Let me implement a method for it. Ternary, we need a simple representation of the ternary. Okay, so we have a string of true branch, and it's going to be a ternary dot, oh, we do not have it here. Okay, so let me create, it's going to have an expression, and let me just make it public, and then it's going to have public, what's going to be the true branch? The true branch is going to be another expression. So public, let's make it final as well, like all the other classes. Final expression, true branch, then we have a false branch after it, and then we have a condition, right? The thing on which this true or false is decided. Condition. All right, we need a constructor. What's the issue? Why do, okay, that creates the constructor for us. That is done. AST printer, true branch is going to be true branch. So true branch is an expression, so I will call the accept method on it with the current visitor, and then we have the false branch. We have the false branch, and then we have a condition. Condition again is a expression, so ternary dot condition dot accept this, and after that I can finally create the string builder and create the string out of it. String builder sb equals to new string builder, and right now I can do sb dot append, and right here, so parenthesize does that for us already, right? So it does that for us. So what we can do is, let me add that on my own. Let me just copy paste. This is boring stuff. Let me just copy paste it. Then we have the false branch. After the false branch, we need to add another parentheses and then return it. That will print the ternary expression for us. And in the parser, where is the error? The error is in ternaries. We are right here. Right here, I can finally create the expression. Token, we do not need that. Yeah, expr equals to new ternary, and I will create the expression out of the expression. That is the condition. Then we have the true branch. Then we have the false branch, and then we have the, why do we need that operator? What all does it take? It takes the expression, true, false, and condition. Sorry, my bad, guys. Instead of this, we do not need it actually. We just need the true, false, and the condition. We do not need the expression right here. It's not required. So expression, and did I add it here? No, I did not. Right. So expression, and then I can finally return the expression. XPR. Does it work? Let me test it. Question mark. So -3, comma -3. So it does work. And then a ternary operator. So true. The condition is true, then I return 1.0, otherwise return 2.0. This is the ternary. Okay, and do the ternaries nest. Yeah, it works. All right, we're good. So let me commit again. Git add, git commit, git push. Should pass the test. And I think all of these, cases, all of these stages should pass now. Does I can proceed to the next one. Mark stage as complete. So I'll just keep clicking through these, and if I see any error, I'll debug it. Otherwise, I think we're good. So let's wait. As you can see, guys, we passed all the stages. So our code works, and the ternary and the comma works as well. But I told you I'm going to remove the comma, right? So let me do that. Instead of going to a comma, it will simply go to a ternary. I don't want the comma because it will cause issues later down the line. So comma should have no usages, and we will simply go into a ternary. And I will remind you again in the future when we come to functions and arguments and parameters where comma would have caused an issue. But remember, it's going to cause an issue way later down the line, so that's why I'm removing it. Anyways, that's it, and I'll see you in the next one.